Hello everyone. Now in the previous chapters we have understood about how to perform static structural analysis. Then we have understood how to perform the modal analysis. In static structural analysis we have done a lot of options, we have covered a lot of options. We have understood how to perform static structural analysis on 3D models, 2D models, 1D models, assemblies. We have seen some important concepts in static structural analysis. Similarly, we have understood how to perform modal analysis. We learned what is modal analysis, why we should perform modal analysis, what do we calculate in modal analysis. We saw different types like free vibrations, free vibrations. We saw how to perform a modal analysis on a 3D model, in 2D models. Then we saw how to perform a modal analysis on an assembly. Okay. Now in today's session, we will be starting with buckling analysis, which is the next chapter that we are going to study. Now, when you talk about buckling analysis, first let us understand what is buckling analysis. Okay. So when we apply static loads on a model, it can produce some instabilities due to some combinations of the geometries and the loads. So whenever we are working on a design and we apply some static loads on it, there can be some situations where due to some combinations of loads or the combinations of loads and geometry, some instabilities can be generated inside the design. Okay, buckling of a long slender bar in the axial compressive direction is a common example that everybody gives whenever we perform buckling analysis. So what is exactly the buckling analysis? So whenever we have a long slender object, now what is the meaning of a slender object? As compared to the length, the cross section of the model is very small. Okay. So a long slender object is nothing but when a body has a length, the length of the body is long as compared to the cross section. So such a body is considered to be a slender object. So when we have such a slender object which is subjected to an axial load, okay, it is subjected to an axial compressive load, what will happen is this object will tend to bend like this. When the force is continuously applied, it will tend to bend more. Okay, after some time it will bend more. But at a particular time, there will be one specific time when the model will completely buckle and it will fail. Okay, so we have to calculate at what load the buckling will occur. Okay, so that is why whenever we talk about buckling analysis, the buckling of a long slender bar is generally taken as the most common example. Okay, so in Ansys Workbench, we will be using the linear buckling analysis system to perform the buckling analysis. Okay. Now let us understand some more things about the buckling analysis. Okay. Now whenever there are thin structures that are subjected to compressive load, this is the same thing that we discussed in the previous slide, that whenever we have a long slender object, so thin structures is nothing but slender object, they are subjected to compressive loads, it can buckle under some loading conditions. Okay, so they can buckle under some load combinations. Now the buckling is a sudden failure of a structure when it is subjected to high compressive stresses, where the actual compressive stress at a point of failure is less than the ultimate compressive stress. Okay, so whenever we are applying some compressive loads on a long slender object, there will be some stresses that will be generated. Okay, so whenever the actual compressive stress at a point of failure is lesser than the ultimate compressive stress, the material will fail, and we have to find out at what value of load will this failure occur. Okay, so that entire thing or that complete concept is called as the buckling concept. Okay. Now when you talk about buckling, there are different cases that we can study in buckling. The first thing is, look at the formula over here. The formula for calculating the buckling load is pi square EI divided by KL square. In this, F is nothing but the critical force or the buckling load, E is the modulus of elasticity, I is the area moment of inertia, L is the unsupported length of the column, K is the column effective length factor whose value depends on the conditions of end supports of the column. Okay, so now we have taken 4 cases of supporting. Okay, now in the first case you will see that the one end of the beam is fixed and the other end is free to move in the lateral direction. So in this condition, if you have such a condition in your design, the K value is considered to be 2. So if one end of the beam is fixed and the other end is free to move laterally, K is taken as 2. In the second condition, if one end is pin supported and second end is also pin supported, if both the ends are pinned, okay, the K value is taken as 1. In the third condition, if one end is completely fixed and the other end is pinned, you can see over here, one end is completely fixed and the other end is pinned, K value is taken as 0.707. And the other condition is, if both the ends are completely fixed, the K value is taken as 0.5. So this is the formula by which the buckling load is calculated, and there are some situation in which the K value will change. So according to the loading conditions and according to the constraining of the other ends, the K value changes. So we have understood what are the situation, under what situations the K value changes. Okay. Apart from this, there are some points that you should remember whenever you are performing a buckling analysis. Now, when you are calculating or when you are performing the buckling analysis will only give us the buckling load and it does not find the area of buckling. So when you perform the buckling analysis, it only calculates the buckling load. It does not show the area in which the buckling will occur. So the output that we obtain from the buckling analysis is only the buckling load. Other points that we should remember while performing buckling analysis is that the linear buckling analysis must always be done after a static structural analysis. That means you first have to perform a static structural analysis and then after that you should follow it by the linear buckling analysis. If you only perform the linear buckling analysis, you will not get your results. Okay, so that is the first point to remember. The second point is the results calculated by the buckling analysis are buckling load factors that scale the loads applied in the static structural analysis. That means the output that you get from the buckling analysis is just the buckling load factor. Now this buckling load factor will scale or will get multiplied to the load that is applied in the static structural analysis. For example, if the force applied in the static structural analysis is 10 Newton, okay, assume that in the beam you have a force that is applied is 10 Newtons, and the result after performing the buckling analysis you get the load factor as 1500. That is the load factor that we have obtained after the analysis. So the buckling load will be 10 Newton, that is the force applied multiplied by the load factor. So the answer will be 15,000 Newton. So 15,000 Newton will be your buckling load. This is a very important thing that you should always know when you are performing the buckling load. Hence, we will always, to simplify the results, we will always apply a unit load in the static structural analysis. That means we apply a load of 1 Newton in the static structural analysis. Why? Because when you apply a load of 1 Newton, whatever load factor you get multiplied by 1 is the same value. So it becomes easy for us to calculate and understand. Okay. The next point is buckling load factor is to be applied to all the loads used in static analysis. That means if there are two loads acting, means if there is one load acting from this direction, the other is in this direction, we will have to apply the load factor to all the loads that are getting applied in the static structural analysis. The next point is there can be many buckling load factors in a structure. Okay, that means you can get multiple load factors. But our main interest is in the lowest buckling load factor. That means whichever is the lowest value in the buckling load factor, that is of main interest to us. That means if you are getting the first 5 buckling load factors, the first one, which will be the lowest one, is the main buckling load factor that we will be interested in. Okay, that is why instead of calculating first 10, first 5 or first 3 buckling load factors, we can only find one buckling load factor, which will be the first one and the lowest one. So we can only take that into consideration. Okay. The last point that you should remember is that the buckling mode shapes displays. The buckling mode shape displays helps us to understand how a part or an assembly will deform during buckling. So once you get the mode shape, okay, of the buckling analysis, we can understand what can be the tentative direction of deformation. But it is not the actual representation of the displacement. So please understand, whatever mode shape you get in buckling analysis can be considered as a example, or it can be considered as a reference, but it will not be the actual displacement that will happen in real time. Okay. So these are some important points that you should always remember when you are performing the buckling analysis.